Forests are some of the most precious and diverse ecosystems on the planet, with tropical forests hosting around half of all known species. Forests also store enormous amounts of carbon, locked away in trunks and branches as biomass. It is essential that we measure the volume and health of our forests worldwide and continue to update our knowledge as our climate changes. In 2025, ESA will launch the Biomass mission, equipped with a world-first orbital P-band synthetic aperture radar instrument to continually map our forests on a planetary scale. The FDL Europe team this year have developed new machine learning workflows that rapidly produce accurate maps of forest structure in 3 dimensions, leading to trusted measurements of our forest ecosystem over time.
Hello everyone, and welcome to the Biomass SAR team presentation. Hello everyone, welcome to the Biomass SAR team's presentation. My name's Grace. I'm really excited to share with you the results of our 8-week research sprint. As Klaus mentioned, our team was heavily inspired by the ESA Biomass mission that you've just heard about, and it's hoped that the result of our project will help to shape some of the data products that might come out of this satellite. The Biomass SAR team is made up of 3 researchers, myself, Grace, Laura and Junpei, and our 2 faculty, Joseph and Carol. I'll start by giving you some background to the challenge before handing over to Junpei and Laura, who will talk about our results. I'd like to start by asking you to take a moment to listen to this sound and think about what you hear. You are listening to the sound of a tree. This is the sound of water moving inside of a tree trunk. These sounds are captured using stethoscopes, such as demonstrated by the lovely Judy Dench here. And we thought these sounds were a really lovely example, a reminder that trees are alive, they are organic matter, they're a form of biomass. And this biomass is primarily stored in forests around the world. Forests are home to millions and millions of plants and animals, with over 60,000 tree species across the world, as well as playing a vital role in the carbon cycle. It is estimated that if forests were allowed to grow and mature strategically, they could increase this carbon drawdown potential to over 200 billion tons of carbon. Protecting forests, supporting carbon removal, protecting habitats of communities around the world, these are such important challenges. And understanding the makeup of forests in terms of tree species can help with biodiversity mapping and tracking the health and resilience of forests over time. So how can we protect them? Historically, satellite data is a really common tool that's been used to track changes to forests over time due to its low cost and global coverage. Historically, this has typically been overhead visual imagery that's been used. However, overhead visual imagery cannot tell you what's going on beneath the canopy. Hence, our project and the ESA Biomass satellite will be using synthetic aperture radar data, or SAR data. SAR data is a longer wavelength radiation that can penetrate the upper forest canopy, as well as being an all-weather imaging system that is not limited by clouds. Leading to our team challenge, using SAR data products to predict forest biophysical parameters. There are 2 data products that we use in our challenge. The first is a kind of 2D SAR image called a single look complex image. The second is a 3D tomographic reconstruction. You're going to hear the word tomographic quite a lot in this presentation. A tomographic cube is a data product that is derived by stacking multiple SAR images, all taken at slightly different angles, and applying a whole lot of processing to create a 3D reconstruction of the scene. These data products can be captured either by satellite or via an airborne imaging system like a plane or a drone. So obviously the ESA Biomass satellite will be a satellite, but a lot of the data that we're using to kind of prepare for the satellite launch is captured via plane. And now I'll hand over to Junpei, who will tell you a bit more about the satellite and more detail about our challenge.
Thank you, Grace. The European Space Agency will launch a new SAR satellite biomass mission, which will be the first P-band sensor satellite. This mission aims to measure forest biomass globally, playing a crucial role in monitoring carbon flux, enhancing the climate change model, and supporting forest management. The satellite will bring SLC data, which will be processed using tomographic SAR analysis to generate 3D data, which we have utilized in this challenge. Challenge is based on a dataset from diverse forests within the Eiffel Park in Germany, dominated by beech, oak, and aspen trees. The necessary dataset was collected using airborne P-band SAR and also LiDAR. LiDAR means airborne laser data, which are remote sensing technologies. By using this airborne dataset, our challenge aims to provide deeper insights into the satellite biomass mission. The provided dataset include training dataset such as tomographic cube, data intensity, and also stack of SLC data, which Grace explained. For ground truth data, we utilize tree height information obtained from LiDAR and also the tree species map taken by field surveys. We have utilized 3 key challenges: tree height estimation, using intensity image as trained data, and tree height information as ground truth, we predict the tree height. And second one is a tree species classification. Here, we used intensity image for training data and tree species information as ground truth data to predict tree species. The third one is a 3D reconstruction. We utilize SLC data as a training dataset and tree height information as ground truth data to predict tree height. So this is our machine learning pipeline. A detailed breakdown will be you can check in the tech memo. In briefly speaking, we just split dataset, applied machine learning models, and estimated both tree height and species. And you know what? Even with these 3 difficult challenges with hard data, we managed to tackle each one. From the next slide, Laura will explain about our results. Over to you, Laura.
Thanks, Junpei. I'm now going to show you our classification model results. In the moving image, you're able to see the different dominant tree species in different colors as results of our model, combined with our height estimation. For the classification model, we obtain an overall accuracy of 75%, which is quite good considering that we're estimating 8 different classes of forests. The model performs better on certain species of trees than others due to data availability. We're now going to show you the results for our height estimation model. We ran the model for each forest type, and you can see that the errors that we get for each class differ based on the data availability. But we still get an overall mean absolute error of about 1.5 meters, with most trees being around 20 meters high. The right bottom map shows the ground truth and the prediction results, and you can see that there is a very good match. The final part of our challenge was to work with the SAR images directly to see if we could recreate the forest heights without the tomographic processing. Our initial results show that high reconstruction is possible, although the high prediction is less accurate than using the tomographic data directly. Given our results, our project will benefit the community for a number of reasons, one of those being the availability of processed data and translated scripts. We have processed classification data through data extraction, LiDAR data through converting between coordinate systems, and Sentinel-2 data through image alignment. The second reason is that we will make available our state-of-the-art models for the classification, height estimation, and tomographic reconstruction. The results that we presented are also very exciting because of the real-world possibility to support the ESA biomass mission, and also for their potential to be generalized on wider set of data to generate a global biodiversity map. Also, if integrated with time series data, our models have the potential to support forest monitoring and also disaster response. We would like to thank our partners and give a specific shout out to Klaus and Francisco for all their invaluable support during this project. And thank you so much for listening and for caring about our forests.